Good afternoon, everybody. I'm William Vickers. I'm a final year PhD student. I'm based down in the dental school, and I also work over at the University of York in their biological tissue research group. As part of my PhD, I've spent quite a lot of time in the materials department here in Leeds working with X-ray crystallography. And I'm going to talk to you today about how we're using X-ray crystallography to develop the materials of the future. So we had a really nice explanation before about how X-ray diffraction works, but basically if you've got, so crystals are formed from atoms arranged in a uniform and repeating structure, and if we fire a coherent beam of X-rays at the sample, we can measure the beam that's refracted off it, and by looking at the interference and the constructive interference that comes from it, we can build up a picture of the spacing of the atoms in a crystal. We've also heard how it's been used in biology, physics, and it's used in chemistry as well, and it's been used for discoveries such as the structure of DNA, for structure of proteins, and it's been used for looking at chemical bonding and the structure of crystals themselves as well. But I'm going to talk to you now about how it's used in materials. And before I came to university, I didn't really know what materials was, and the science of it is quite often described as material science and engineering. So you've got the material scientists who are interested in the relationships between structures and the properties of the materials. Whereas the engineers who apply this, and they apply this knowledge to make a material that has the properties tailored to a specific application. And the two overlap. I wouldn't really class myself as one or the other. But just out of interest and for a bit of fun, I did a Google image search for a materials scientist and a materials engineer. And this is what we got. So we got the material scientists who are interested in the structure and the position of the atoms and what's going on. And then the engineers who apply it and they make materials from it for a specific application. And material scientists are interested, and materials engineers are interested in X-ray diffraction because a lot of the materials that we use are formed from crystals. So nearly all metals, apart from some specific engineering examples, are crystals. Ceramics are formed from crystals, and polymers can have crystals in them as well. So not all ceramics are. We have glass as well, which is amorphous, and they can also be both amorphous and crystalline. In fact, crystallography is such an important part of materials. The final image search before I did some work. And so I googled material science, and this is the first 3 rows of images that came up. And barring the two, we've got a biological example there and then an atom, all the other examples are examples of crystals. And in fact, if we look at this here, this is material scientists trying to explain materials in terms of crystal structure. So it really is a key part of material science. And what we've heard about so far is mainly techniques on single crystal diffraction, and this allows us to measure the positions of atoms in a crystal of an unknown material and see the positions of it, the dimensions of the unit cell it's called. But most of the materials that we use, they aren't single crystals. They're formed from lots of small crystallites, and these can be different sizes, they can be different orientations, and they can be different compositions. This is an image that I took with one of my colleagues, and it's of a ceramic coating for dental implants, and you can see the variation just in this image alone of the variation in the crystal sizes, the shape, and also the orientation of it. So single crystal diffraction isn't suitable for us to use, and instead we use a technique called powder diffraction. This is a piece of equipment I use. This is Philips Expert. This is in the materials department. And its actual setup isn't really that much different from what Bragg was using. So you have an X-ray source here, you have your sample, and then you have a detector, and the two of them move around the sample and take measurements at different angles. And what this produces is a powder diffraction pattern. And so as I said before, we can't take direct measurements of the positions of the atoms, but we can match this diffraction pattern to a database of known patterns. It's much like how a criminal's fingerprint would be matched to a database, and we could find out who they are. And the position of these peaks all indicate different spacing between different planes in a crystal. And some crystals, as I said before, not all the materials that we use are formed from one crystal, and they're not formed from necessarily crystals with the same composition. So this one, for example, has actually got 2 different crystal phases in it, so we can see the peaks for one and the second. And we can tell the quantity of each of these crystal phases in the material by looking at the intensity of the peaks, the height of them. But we can gain a lot more information from this as well. So by looking at how the position of the peaks change, we can see how the size of the spacing between the crystal planes is changing. And also, by looking at the shape of the peaks, we can get information about the stresses that might be in the material. This could be induced from changes in shape of the crystals. We can also see if the composition is consistent, not just through through multiple crystals, but maybe one crystal has variations in composition as well. And this changes the shape of the peaks. And in fact, this is where for me anyway, the big advancement in X-ray crystallography for powder diffraction anyway has gone, because we're not just gaining these patterns anymore. Thanks to computers, we can actually simulate models of virtual materials, virtual crystal structures, simulate scans from them, and then if that matches our data, then we've got a rough idea that our model, our virtual model, is what we've got. So we can take a powder diffraction, a known crystal, change it until we've got what we've got, and basically see the creation of new materials. And why is this important? This is just an example of how the crystal structure might change, and also the change in peak shape. So this is cold rolling of copper, and at the start you've got uniform crystal shape, but then when it's rolled, the crystals are now elongated, and we can detect this using powder diffraction. And this actually induces stress in the material, as I was saying before. Imagine bending a ruler, you put force and you put energy into it, and then when that stress exceeds the limit of the material, it breaks. And this is important because we'll see this later. And currently, X-ray diffraction is the only technique that can be used for measuring the actual strain within the crystals. And all these properties are important because it's the size, the shape, the composition and the structure of the crystals, as well as the stresses and the changes in composition that determine the material's properties. It might be how it fails, its strength, its corrosion resistance, and even its ability to conduct electricity. So I'd like to give an example now of how this is applied by materials engineers, and this piece of work was done by one of my colleagues, Tim Cumming, and his group in the materials department. And I'd say this is a material of the future because it's going to shape our world. So this is a technology used for carbon capture. Burning fossil fuels produces carbon dioxide. This might be from your cars, or it could be from factories, and this is just released into the atmosphere. And this contributes towards global warming and other environmental effects, such as acidification of the oceans, which is destroying coral reefs around the world. And so the big problem is how do we collect this carbon dioxide? And then also, what do we do with it? So people have come up with ideas of, once we've collected it, we could pump it underground and store it. We could use it for extracting methane and extracting more oil to produce more carbon dioxide, which doesn't completely make sense to me, but that's one of the things they're doing with it. But the problem is, how do we capture it? One of the technologies that's used are calcium oxide particles, and these particles are formed from multiple small crystallites, and this is important, as we'll see later on. But the technology basically involves putting these particles in the flue, in the chimneys of the factory, and then when the waste gases pass through, so they contain carbon dioxide, water vapour and other flue gases, they react with the particles and they carbonate it, and so you get calcium carbonate, and then the remaining gases are released into the atmosphere. These particles can then be collected, and we put them in a chamber, and if we heat them, they calcine, and they release carbon dioxide, which can be collected, stored, or used for other applications. But it also converts the calcium carbonate back into calcium oxide, which can then be reused. But with repeating cycling, we actually see the efficiency of this process being reduced. And the theories behind it, well, the first one is that when the particles are heated, they sinter. So they go from being these individual particles and they coalesce. And when they do this, they lose surface area. And this is important because it's on the surface of the material where the reaction takes place. And if we lose this surface area, then the reaction becomes less efficient. And it's also thought that the particles break down. Again, so they lose the ability to perform to remove the carbon dioxide. So Tim Cumming and his colleagues, they looked to X-ray diffraction to try and explain why this was happening. And if they could explain it, they could improve the process and make it more efficient. And they used the diamond synchrotron source to take inline measurements of the particles while they were exposed to carbon dioxide and see what was happening to them. So they were also interested as well in maybe looking at an alternative to calcium oxide. And so they looked at calcium hydroxide. Now this isn't as readily available and not as easy to use, but they wanted to see what was happening with it anyway. And so along the bottom we've got temperature, and then along the x-axis we've got the amount of calcium carbonate in the material. As the temperature increases, the amount of calcium carbonate increases. But in the example of calcium oxide here, and this is a wet sample of calcium oxide, it peaks at around 800 and you get around 70% efficiency on it. So the process could be improved, and they wanted to see what was going on with this. And by using X-ray diffraction of the powdered samples, they could actually see that there were two peaks occurring. This is from a calcium oxide particle that's been exposed to carbon dioxide. And what they see is that you get this very sharp, well-defined peak for calcium oxide. But you get these broad peaks forming on it as well, and these are for calcium hydroxide. So the fact that the peaks are broad indicates a couple of things. It's that the particles that are forming on the surface, the crystals are very small, but it's also that they're stressed. And so they went on to try and develop an idea of what was going on and why the material was failing. And it turned out that the calcium oxide core was forming a calcium hydroxide layer on the outside of it, and this was preventing the whole of the calcium oxide from reacting, and again, a loss in efficiency. But then going further and looking at the stress of the material, from analysing the width of the peaks, they actually found that the stress in the crystals that was forming was nearly 10 times that of what the material should be able to take. And so the layer was breaking off and the materials were degrading. And so using this technology, they apply it, and you can increase the efficiency of carbon capture. And again, I think this would have a big impact on the world that we live in. The next example that I'd like to give is my research. So I'm a tissue engineer. Initially I was a material scientist, but I've learnt some biology, and I'm kind of trying to apply material science with biology, meet in the middle, learn the two languages, and basically help tissues regenerate. And I focus on bone. So a lot of people know that bone's got calcium in it, but there's a lot more to it than that. If we look, it's got cells, and cells sit on a material which they call the extracellular matrix, and this is the environment that they live in. And the extracellular matrix is composed of collagen fibres with these crystals of hydroxyapatite that sit within it. And this is important because we can use X-ray diffraction to analyse these crystals and also develop alternatives for them so that we can make a replacement material. Bone has is able to self-heal, and it can heal without scarring, and this is important. But in some instances, so we call it non-union fracture, let's say there's bone missing, it might have shattered off in a motorbike accident, or you've had it removed due to disease, the bone won't heal by itself, and so we have to help it. And we implant a material that can do this. And tissue engineers are interested in doing this, and they take a material, they apply cells to it, and they implant it, and they can then take a non-union fracture like this and help it to heal fully. And they do this using a material called a scaffold. And a scaffold in tissue engineering is a lot like a scaffold in engineering. So scaffolds support workers while they build up in 3D, and they build height, and they put the bricks and mortars down to build a house. They can build a 3D structure. Well, a scaffold in tissue engineering does the same for cells. If you were to grow cells by themselves without a scaffold, they just grow flat on a 2D surface. You wouldn't be able to build 3D tissues. But with a scaffold, we can support them while they lay down their own extracellular matrix, and then once the matrix is laid down, the scaffold is resorbed. It doesn't need to be removed with surgery, it's naturally resorbed. And this is a picture of one of my scaffolds. And these features here you can see, these are all stem cells that I isolated from somebody's bone marrow, and I seeded onto the material. And as we'll see later, we can actually make them lay down their own bone. So the material that we use, it has to be strong like bone. Bone supports our bodies, but it also has to be able to communicate with the cells and tell them what to do. Bone healing first starts with stem cells in your bone marrow, they're called mesenchymal stem cells, migrating to the site of injury. And stem cells are important because they can form different tissues, they can form different cell types, but they need to be told what to do. And the way that we tell them what to do is through chemicals, but also which interact with receptors on the surface of the cells, but also using physical cues. So the shape of the material that we use is important, that can tell a stem cell what type of cell it should become, but also using surface features. So the sites where the cell adheres to the material, by changing the position of them, by changing the spacing of them, we can direct a stem cell down a certain route. We can tell it to become a muscle cell, or we can tell it to become a bone-forming cell. And the material scientist, I can take all this information, and I can use crystals to form a material that has the properties that we want. It can have the chemical properties that we want, it can degrade at a certain rate and release the chemicals when needed, but it can also have these surface properties that can direct a cell physically to become a bone-forming cell. Now I do this using glass, and glass isn't actually crystalline, it's amorphous. It's got the same composition as a crystal, but the atoms are arranged like in a liquid. They don't have this repeating uniform structure. And to give the cells the chemical cues that we need, we add in the chemicals that you find in bone. So we take glass, like silica, like you have in windows, and we add calcium, we add magnesium, phosphorus, and fluorine into it. We mix them all together, and we heat them up in a furnace at 1,450 degrees C, take them out, and we pour them, it's called shock quenching, into cold water. And this freezes them in the amorphous, almost liquid state, but it's a solid. I really enjoy doing this. This is just done in the dental school in just like a small little room off the side, and you would never know that all this is going on. And it's pretty dangerous. We have to wear fireproof suits and all. I love it. It's like the best part of my work. But we can take this glass, and And the amorphous structure isn't the most stable structure it could be. The crystal structure is more stable, and it wants to form a crystal if it can. And by putting in a little bit of heat, we can make the glass transform into a crystal. And by using X-ray diffraction, we can see what crystals form using different heat treatments and using different chemicals, and we can tailor a material to have the properties that we want. This is what the glass particles look like. So they're really small, they're about 1/10 of a millimetre, and they're small like this because we grind them up and then we put them into moulds and we form porous structures like bone. This is a figure from my thesis, and what it shows is a series of powder diffraction traces of the glass, and then the glass following different temperature heat treatments. And at the bottom, this is what a powder diffraction trace for glass looks like, and it doesn't have these well-defined narrow peaks that you'd see for a crystalline structure. It has this broad peak here, and this is due to the fact that the coordination of the bonds are the same, but the atoms aren't in this ordered structure. But as we heat it and we put energy into it, and the atoms are able to move around, they then start to form these crystal structures, and we can see these very well-defined peaks. And as we increase the temperature, we see different peaks forming, and these are different crystal phases. And by using X-ray diffraction, we can see what these crystals are. We can see their shape. By looking at the shape of the peaks, we can see if the crystals are stressed, if the composition changes throughout them, and then apply all this knowledge to form a material that has all the properties that we want. And this is the final result. This is one of the porous bone scaffolds that I've made, and you can see on the surface it's got these long rod crystals, and these act like reinforcement for the material. They give it its strength. They're like the steel bars that you get in reinforced concrete. They hold it together and they give it the mechanical strength that it needs as a bone replacement material. But if we zoom in, you see it's also got these small crystals, and these direct the cells not only chemically as they dissolve, but also in the way that they're positioned in their arrangement. This is like how I said previously, how by changing the attachment sites we can direct cells down different routes. And all this was developed using, obviously there are other techniques as well, but it was the X-ray diffraction that I used to actually develop the crystals. And without X-ray diffraction, this wouldn't have been possible. And this is just the example of it being used. So this is the bare scaffold, and then this scaffold here is one that I've seeded mesenchymal stem cells onto, that I extracted from a patient's bone. I didn't do it myself, but that we've isolated from a patient's bone marrow. So we actually, I do extract them from the bone, but what happens is when somebody goes for a total hip replacement or a knee replacement, we've given the surgeons some special pots, and they take the bone that they've taken out and they put it in the pot. We take it to the lab and then we scrape the bone marrow out, and then by a series of steps we actually extract the mesenchymal stem cells from that. And we seed them onto the material, and as you can see they cover the material, they're quite happy with it, they proliferate on it is what we say in biology, something I've learnt doing biology. And we can see here for a gap in the material that the cells, they do actually interact with the material as well, and by doing a series of biochemical assays on it, we can see that they're not only transforming into bone type cells, but they're also producing their own bone. So the idea is that a material like this could be implanted into a non-union fracture and speed up the recovery rate. And I'm not the first one to do this, there's lots of materials like this out there already, but by using X-ray diffraction we've optimised the process and hopefully reduced the recovery time. So that's the end of my talk, and as you can see, X-ray diffraction really is a key part of defining the materials of the future. And we've seen already it's a key part of so many other disciplines as well, and like probably nearly everyone else I'd imagine, I'm going to push that you all go and vote for it for the most important innovation of the last 100 years. And X-ray crystallography, when you click on it, is right at the bottom, so you have to scroll all the way down and find it. But apparently, yeah, we're number one at the moment. I was a bit worried because Mini Cooper was ahead of us, which I kind of felt a bit bad, because without X-ray crystallography, they wouldn't have all the metal technology that they have in it, so it's a bit unfair that Mini was winning. But yeah, apparently we're winning now, so let's try and keep it there. Thank you very much, everybody, for listening. Yeah, it was a great opportunity to come and talk to you all.